cost minimization with varying output level. So in earlier slide, we studied the cost minimization solution when Q equals some 100 pence a pizza, right? Also then, what happened? We can also solve cost minimization problem when Q equals 101, 110. Also, we can also solve cost minimization problem again when Q equals 200 like this. Anyway, in earlier graph, we can find some equilibrium point for every unit output of production level, right? If we connect all of these optimal points, right? That is cost minimization with varying output level. That is expansion path. Curve passing through points of tangency, optimal bundles, optimal input mix of labor and capital between the firms, ISO cost line and each ISO quants. The firm can hire labor L, blah, blah, blah. Our wage rate is $10, rental rate of capital stock is $20. Given this input cost, we have drawn 3 of the firm's ISO cost line. Each ISO cost line is given by the following equation. Anyway, slope of expansion path should be equal to half. Right? I'd like to explain a little later for this. The expansion path and long-run cost. To move from the expansion path to the cost curve, we follow 3 steps. Choose an output level represented by an isoquant, then find the point of tangency that isoquant with the ISO cost line. From the chosen ISO cost line, determine the minimum cost of producing the output level that has been selected. Number 3, graph the output cost combination in figure 7.6. Okay? Now think about when pizza production is 100, you can find optimal input mix at point A. At that time, at here, labor employment is 50, capital employment 25. Right? Then we can calculate the minimum cost at point A. Like this. Also, when you produce 200 pence of pizza, then some ISO cost line is this one. Right? ISO cost line is this one. And there are lots of ISO cost line. I'm sorry, this is isoquant is this one. Subject is subject to this one. There are lots of minimizing cost, right? Rewriting this. Capital is cost over R, W over R, L. Subject to Q equal 100, for example. Solution of this one is occurred at point A, right? And if this one is 200, then this subject isoquant curve shifted to this one and you find solution, new solution when Q equal 200. That happened at point B, right? And when you produce Q equals 300, then you can find optimal input mix at point C. If we connect A, B, C, then we can get this kind of expansion path. That is expansion path. Okay? Also from here, we can derive minimize cost. When you're producing 100 pence of pizza, you hire 50 labor, right? 50 labor plus 25 capital stock. That is minimized cost. Minimized cost for 100 pence of pizza. Minimized cost for 100 pence of pizza, isn't it? And we know wage rate is $10. Rental rate of capital stock is something. Then total cost is something. Right? At point A. Also think about at point B, total cost is equal to wage rate $10, rental rate of capital stock 20, labor employment is now, I cannot see, 150. Right? Labor employment is 100 and this one is 50. Then total cost can be minimized total cost to when you produce 200 pence of pizza, calculate this. Right? And at point C, so we can continue this one. Then we can get when you produce Q equal 100 pence of pizza, minimize total cost. This one is here, for example, right? And when you produce 200 pence of pizza, minimize cost, what happens? That is here like this. At point C, when you produce 300, also you can calculate the minimized total cost. If we connect this up, we can get this kind of total cost curve. Right? So total cost curve is actually minimized total cost as a solution of cost minimization problem at each production level of Q. That is this one. Right? That is cost curve. So I explain how minimized total cost or simply total cost is derived from cost minimization problem. Next slide, example. Reducing the use of energy. Y variable is capital, X variable is energy. Right? Energy efficiency through capital substitution for labor. Greater energy efficiency can be achieved if the capital is substituted for capital energy. This is shown as a movement along the isocontour Q1 from point A to B. Right? At point B, energy use decrease compared to equilibrium point at A. But capital employment increase. Capital use increase. Energy use decrease. So substitution happen. Energy efficiency, energy saving through capital substitution for labor, like this. This is shown as blah, 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 right? Now we go next example. But there is other way to reducing the use of energy. That is energy efficiency through technological change. Earlier one was energy efficiency through capital substitution for labor. Capital used widely, more widely, right? But section 2 is energy efficiency through technological change. Original equilibrium condition cost minimization solution occurred at point E. ISO cost line Q1. But technological change happened. Then, so ISO cost line is simply this kind of thing, isn't it? Right? This curve is this one. But production function, we know that there are other factors. One of the important shifters of this production function is technology level, right? This one increase. Then what happens? You can produce same unit of Q1 with smaller employment of energy and capital simultaneously. That is energy efficiency through technological change. Okay? 32. Now we're moving section 4. Long-run versus short-run cost curves. The inflexibility of short-run production. The inflexibility of short-run production. When a firm operates in the short-run, its cost of production may not be minimized because of inflexibility in the use of capital unit. Originally, in the short-run, now you solve Q1 is something and minimize ISO cost, total cost or minimize ISO cost line is this one. So optimal input mix is L1 and K1. In the short-run, you want to produce 100 pence of pizza to 200 pence of pizza, right? But in the short-run, so capital is same, capital employment same. So if you want to produce 200 pence of pizza, you have to move point P, right? Your only way to produce more pizza is increasing labor employment, holding capital employment constant, right? Then at point B, you can draw ISO cost line crossing point B, and as we know, the intercept of Y is indicates magnitude of total cost, right? So total cost in the short run is like this. But in the long run, what happens? Capital is not fixed variable. Capital is average, not fixed, can vary, right? Then long-term solution should be here to produce same 200 pence of pizza at this point because we can hire more capital than short run, right? Now, we know that cost minimization point should be here, and you can draw minimize ISO cost line tangent at this point. That is this one. Then, at this point, total cost, minimize total cost indicated by y-intercept. That is OC, right? Shonen cost to produce 200 pence of pizza was OE, right? So total cost decrease in the long run compared with shonen cost. Can you understand? That is explanation of figure 7.8. Long run average cost. In the long run, the ability to change the amount of capital allows the firm to reduce costs. We already studied, right? The most important determinant of the shape of long run average and the marginal cost curve is the relationship between the scale of the firm's operation and the inputs that are required to minimize each cost. Long run average cost curve. Curve relating average cost of production to output when all inputs are variable. That is long run average cost curve. When capital is also variable. Simply talking in two-factor model, right? Shown on average cost curve. Curve relating average cost of production to output when level of capital is fixed. Long run marginal cost curve. Curve showing the change in long run total cost as output is increased incrementally by 1 unit. Okay? So look at this. Long run average cost curve. Long run average cost curve is shaped like this. And long run marginal cost curve is like this. Long run marginal cost curve cross minimum point of long run average cost curve. Right? Actually, you studied this in Mankip's Introduction to Economics book. When a firm is producing at an output at which the long run average cost is falling, long run average cost is falling, right? Long run average cost is falling, the long run marginal cost is less than average cost, right? So, long run average cost falling. So, for example, long run average cost, and that is long run marginal cost, long run average cost. Long run average cost falling, then what happens? That happens when you place 0 to this unit. Here, what happens? Long run average cost greater than, long run marginal cost smaller than long run average cost. Okay? This one is explained here. The curve intersects at point A where long run average cost achieves its minimum, right? So long run average cost reaching a minimum point or constant. In that point, this one is equal to like this. Or long run average cost increasing. So this area, long run average cost increasing. Then what happens? Long run marginal cost curve greater than long run average cost curve. We can see this kind of relations. Economies and diseconomies of scale. As output increases, the firm's average cost of producing that output is likely to decline. N is 2 point. So economies of scale means sort of this one, right? It said economies of scale means long run average, decreasing in long run average cost. Output increase, the firm's average cost of producing that output is likely to decline, right? At this economies of scale. This can happen for following reasons. If the firm operates on a large scale, workers can specialize in activities in which they are most productive. One labor just specializes in one task, for example. If the size scale is very small, one worker do lots of tasks, purchasing pizza, cooking pizza, and delivering to customers, for example. But size increase, scale increase. One worker just focus on delivery. The other worker just specialize in cooking pizza like this. Number 2, scale can provide flexibility by varying the combination of input utilized to produce the firm's output. Managers can organize the production process more effectively. Organization by managers become more effective. if there are some scale. Number 3, the firm may be able to acquire some production input, for example, flour or sausage, at a lower cost because it is purchasing them in large quantities than before. Okay? And therefore negotiate better price. The mix of input might change with the scale of the firm's operation if managers take advantage of low-cost input. Okay? And at some point, however, it is likely that average cost of production will begin to increase when production increase, right? So this one means this economies of scale. This economies of scale. Why that happen? Number 1, unless in the short run, factory space and machinery may make it more difficult for workers to do their job effectively. Think about pizza restaurant, right? One labor combined with 5 capital oven to cook pizza. Now you hire lots of some laborers. Then 100 labor combined with some 10 capital oven. Some lots of congestion problem happen, right? So that kind of thing happen. Number 2, managing a large firm may become more complex and inefficient as the number of tasks increase. Number of tasks increase exponentially. So one manager has to involve in so many tasks, so inefficiency happen. Number 3, the advantage of purchasing in bulk may have disappeared once certain quantities reaches. At some point, available suppliers of key input may be limited, pushing their costs up. In the earlier slide, more purchase of some material leading to decrease in price, right? But if you limit some point, critical point, it increase price, right? Intermediate goods price. That is number 3. Then this economies of scale happen. Economies of scale situation is output can be doubled for less than doubling of cost, right? Situation where output can be doubled for less than a doubling of cost, right? Output can, for example, output doubled, cost doubled. How can I say? Cost doubled, output more than doubled. That is economies of scale. This economies of scale, cost doubled, output less than doubled. Okay? Then this kind of thing. That is this economies of scale. A firm enjoys economies of scale when it can double its output for less than twice the cost. The terms economies of scale includes increasing return to scale as a special case. But it is more general because it reflects input proportion that change as a firm changes the level of production. Right? I'd like to add something for here. I already explained for this, right? So economies of scale measured by output versus in cost, right? Cost, output doubled, cost less than doubled, or cost doubled, output more than doubled. That is economies of scale, and vice versa, right? So, and now think about increasing return to scale. Increasing return to scale means input doubled, output more than doubled, right? That is the definition of increasing return to scale. Economies of scale means output more than doubled when cost doubled. So that is cost. In increasing return to scale, that is input, right? But cost, input doubled, cost increased. But also the relative price of factor matter. Think about cost minimization. And substitution of labor and capital happen. Right? So this is a more general term than increasing return to scale. That is explained here. A firm enjoys economies of scale when it can double its output for less than twice the cost. The term economies of scale includes increasing return to scale as a special case. That this one is a special case of this. Right? Only focus on input, but this is more general. So cost change also consider input changes plus substitution between input, right? Because economy scale is more general because it reflects the input proportion that changes as the firm changes the level of production. Increasing return to scale, output more than double, blah, blah, blah. Economy of scale, like this, right? That is economies of scale, right? And economies of scale are often measured in terms of output elasticity of cost. Output elasticity of cost. Now think about what is output elasticity of cost. So our textbook said cost output elasticity. More exactly speaking, that is output elasticity of cost. Output elasticity of cost. Now think about price elasticity of demand. Right? Similarly, output elasticity of cost. That means percentage change in cost over percentage change in output. Right? That is the definition of cost output elasticity or output elasticity of cost. Right? This one means change in C over change in Q. Output change. Output is Q. Right? Multiplied by Q over total cost. Right? You can write this. Right? And now you're familiar with this. What is this? That is definition of a marginal cost, isn't it? Right? That is equal to marginal cost. And what is this? Q over C. Reciprocal value of C over Q. C over Q is average cost, isn't it? Right? This one is this one. Q over C is this one. So in sum, we can write marginal cost over average cost. That is output elasticity of cost. Okay? That is explained here. Thus, if our textbook, this one just said EC, right? So if EC, now think about first case, EC is equal to 1. That means marginal cost equal to average cost, right? Marginal cost equal to average cost. That means, so how can I say? That is 1, right? Then this point, for example, right? Or two things are same. Now, second case is economies of scale case, right? Then EC is like this, right? This one is less than 1. Less than 1. That is positive number, less than 1. That means average cost is greater than marginal cost. Average cost is greater than marginal cost. Okay? So this case, isn't it? So that means economies of scale. Economies of scale, right? Long run average cost decreasing, then average cost greater than marginal cost. Right? EC is higher than 0, less than 1. Then average cost greater than marginal cost, or average cost decreasing. So economies of scale. Can you understand? And the other case is average cost, EC is greater than 1. EC is greater than 1. That means this is higher than 1. That means marginal cost higher than average cost. Marginal cost is higher than average cost. Right? Marginal cost is higher than average cost. That is this economies of scale. This economies of scale. Can you understand? That is explained here. Right? clearly EC is equal to 1 when marginal and average costs are equal, right? This case. In that case, costs increase proportionately when output, and there are neither economies nor diseconomies of scale. When there are economies of scale, when costs increase less than proportionately with output, marginal cost is less than average cost, and EC is less than 1, right? Is this one, economies of scale. And finally, when there are diseconomies of scale, marginal cost is greater than average cost, and the EC is greater than 1. Okay? And I'd like to add one more thing. SCI, right? So scale economies index. So scale economies index. Later part of our textbook introduces scale economies of index. Right? Scale economies of index. This one is defined by this one. I'm sorry. This one is defined by 1 minus EC. Am I correct? Right. Like this. Right? Then, economies of scale, that is higher than 0, less than 1. Right? Then 1 minus 0 point something. So SCI, positive. This one is same thing. Economies of scale is positive. Positive economies of scale, then EC. Right? Output elasticity of cost is higher than 0, less than 1. And then what happens? EC is higher than 1. SCI is negative. SCI, scale economies index, is negative. Right? So this is economies of scale. Okay? So I introduce output elasticity of cost, or cost output elasticity like this. And define EC. These three cases. Also, I introduce scale economies, scale index, right? Economies of scale index, 1 minus EC, then this one. This one is same to this one. This one is same to this one. Okay? Okay, I'd like to stop here 1 minute and we go example. Okay, example, the effect of effluent fees on output choice. Okay, I'd like to skip this and we go next section. Long run versus short run cost curve. The relationship between short run and long run cost. Right? Long run cost with economies and diseconomies of scale. The long run average cost, LAC, is the envelope of short run average cost curve. SAC1, SAC2, short run average cost 3. So this figure is perfectly same to the contents of Mankew's Introduction to Economics. With economies of scale and diseconomies of scale, the minimum points of short run average cost do not lie on the long run average cost curve. Right? The short run average cost here in SAC1 is the right-hand side of long run average cost curve. But here, the minimum point of short run average cost curve is left-hand side of some long run average cost curve, like this. And now we go production with two output. Production with joint output with cell. So think about production possibility frontier when there is two good produced. That is same concept, right? We said economies of scope. We already started economies of scale. More production is more efficient. That is a summary of economies of scale. Sometimes economies of scope, right? So think about this. Product transformation curve or production possibility frontier, right? Product transformation curve showing the various combination of two different output that can be produced with given a set of input, labor and capital input, right? So joint output of factors. The product transformation curve describes the different combination of two outputs that can be produced with fixed amount of production input. The production transformation curve O1 and O2 are both concave because there are economies of scope. Right? Economies of scope. So then, what is economies of scope? The economies of scope and diseconomies of scope. Economies of scope means a situation where a joint output of a single firm, one firm produces two goods, right? Situation where joint output of a single firm is higher than output that could be achieved by two different firms, right? Each firm produces a single product, right? So one firm produces joint output is more efficient than two goods produced by separate two firms. That is economies of scope. Okay? This economies of scope, situation in which joint output of a single firm is less than could be achieved by separate firms when each produces a single product. The degree of economies of scope is like this, right? SC is economies of scope. Economies of scope. I'm sorry. Economies of scope, not scale, scope, right? So EC or SC. I'm sorry. Economies of scope is defined by the Q1 plus cost producing Q2 by separate firms, right? This is a total cost when two firms produce two goods separately, right? It's total cost of by two firms. And what is this? Cost Q1, Q2. That is total cost, right? Total cost of two goods when one firm produces two goods, right? Divided by C Q1, Q2, right? That is the scale economies in scope, economies of scope index, degree of economies of scope, degree of economies of scope. If this is positive, in other words, total cost by two firms, each producing each good, higher than some cost, total cost of one firm when one firm producing two goods. That is positive. This one is more cost than this. Right? In other words, joint production by one firm is more efficient, cost-wise. Right? So if that is positive, we said economies of scope exists. Percentage of cost saving resulting when two or more products are produced jointly rather than by individually. Right? So that is positive. Economies of scope exists. In other words, joint production by one firm is more better than production of two goods by two companies. Okay, that is economies of scope. I'd like to skip this. Okay. So economies of scope. That is economies of scope. So I emphasize that the importance of economies of scale. Also, economies of scope is also very important when we study long-term economic growth, right? So economic growth means more production happen, more consumption happen, right? Why that happen? Number one, I said technological change or something. One specific form of technological change in the long run is economies of scale. One firm, some firm now produce more goods than before, then productivity increase. The size, production size really matter. So the larger, right, the more efficient. The bigger, the more efficient, simply talking. That is economies of scale. That is really important sources of long-term economic growth or productivity growth. The second reason is this one, economies of scope. Economies of scope. Now think about, that is another source of long-term economic growth. So one famous economic historian in Harvard University said, if we look at long-term development of capitalist economies, we can see two important sources. That number one, economies of scale. Number two, economies of scope. Okay? And example, economies of scope in the trucking industry. I'd like to skip this. And now we go dynamic change in cost, the learning curve. We studied learning curve, dynamic change in cost. In earlier graph, we said production increase, then average cost decrease, for example, right? We said this is economies of scale. The bigger, the beautiful, the more efficient. Okay? And here, dynamic change, dynamics or learning curve is this kind of thing. Average cost decrease when sigma q, accumulation of production increase. Right? That is dynamic curve, learning curve. That is economies of scale. This is dynamics. Okay? As a management and labor gain experience with production, the firm's marginal and average cost of producing a given level of output for reason. Reason for the dynamic changes in cost. Number one, workers often take longer to accomplish a given task the first few times they do it. As they become more adapted, more experienced, their speed increase. Right? Number two, managers learn to schedule the production process more effectively from the flow of materials to the organization of the manufacturing itself. Engineers who are initially cautious in their product design may gain enough experience to be able to allow for tolerances in design that save costs without increasing defects. Better and more specialized tools and plant organizers may also lower costs. Number four, suppliers may learn how to process required materials more effectively and pass on some of this advantage in the form of lower costs. Okay, that is learning curve. Graph relating amount of input needed by a firm to produce each unit of output to each cumulative output. Right? So this learning curve is another important source of productivity growth. For example, you study Microeconomics Chapter 2. So it's really difficult. You see some new concepts, right? So, but you study Chapter 2, Chapter 3, and Chapter 4, and now you study Chapter 7. Your experience, accumulated experience increase. It's really easy to study Chapter 7 like this. That is learning curve. Okay? Look at this. Graph the learning curve. Y variable is hours of labor per production unit. And that is cumulative experience, cumulative production like this. Decrease. We said this is learning curve. A firm's production costs may fall over time as managers and workers become more experienced and more effective at using the available plant and equipment. The learning curve shows the extent to which hours of labor needed per unit of output fall as the cumulative output increases. The learning curve is based on the relationship like this. And for example, mathematically, L is equal to A plus B, Bn minus beta, Bn minus beta, for example, like this, right? Then we can graph this kind of thing, right? So usually economists use logarithm. Then we take the log, then log L, the natural log here. Log L is equal to log A is just disappeared, for example. Then log Bn minus beta, right? That means minus beta moving here. Then minus beta log Bn. B is constant numbers, N is constant numbers like this. Right? Learning curve. Learning versus economies of scale. The difference between learning versus experience of scale. Now, y variable is not accumulated output, just output. Right? So, average cost decrease like this. That is economies of scale, isn't it? Right? Q increase, average cost decrease. That is definition of economies of scale. Then what is learning curve in this graph? A firm's average cost of production can decline over time because of growth of sales. When increasing returns are present, or move A to B on curve AC1. That is economies of scale. Or it can decline because there is a learning curve. Moving A to B is economies of scale, but average cost shift downward like this. Then you moving A to C. That is learning. Okay? Or it can decline because there is a learning curve. Move from A on curve AC1 to C on AC2. That is learning. When this variable is output instead of accumulated output. That is data. Some example of firm producing machine tools know that its labor requirement per machine for the first 10 machine is 0.1. When you're producing up to 10 units, then average cost is 1. So total labor cost, requirement is 10 multiplied by 1, so 10. Okay? When you produce next 10 output, so accumulated output is 20, then what happens? 10 to 20, average cost is 80 cents instead 80, 0.8 instead of 1. Then, so total labor requirements is, when you're producing 10 units, 10. So we said 10 plus this one multiplied by next 10, right? So 18. When you're moving this side, another 10, so accumulate output is 30. Unit labor requirement is 0.7. So first 2 units, $18, plus 10 multiplied by 0.7, so 7 like this. Okay? Next is 250 plus this one multiplied by 10 like this. Can you understand? Right? That is total labor requirements. The numbers in this column are calculated from the equation. Log is, for example, here, n is 10 in this example, right? So from here I said n. N is, B. B is 1/10. Now think about B equal 1/10. Then we can say like this, right? Then here log L is beta is 0.322 like this, right? Log n over 10, where L is the unit labor input and n is cumulative output, like this. This is the curve, right? Starting from here in earlier section. Learning curve in France. Learning curve effects can be important in determining the shape of long-run costs and can thus help guide management decisions. Managers can use learning curve information to decide whether production operation is profitable, and if so, how to plan how large the plant operation and the volume of cumulative output need to be generate a positive cash flow. The learning curve relates the labor requirements for aircraft to cumulative numbers of aircraft. That is cumulative numbers, right? I cannot see. It's too vague. So more production, lowered, I think. Okay, I'd like to skip this. And we go 49. Estimating and predicting cost. cost function relating cost of production to level of output and other variables that the firm can control. Variable cost curve for the automobile industry. So, for example, there are famous car manufacturers, right? And each firm's, for example, Chrysler's production of car is like this, variable cost is like this. Volvo's cars and variable cost is here, okay? Honda, no, car production and Y variable is variable cost of Honda, right? Nissan's variable cost and Nissan's car production like this. So there are 2, 4, 6, 7 companies. Using this actual data, we can project fitted value like this. Positive relationship between more production, variable cost increase, right? That is estimated by econometric technique. Okay, to predict cost accurately, we must determine the underlying relationship between variable cost and output. The curve provides a reasonably close fit to the cost data. But what shape is most appropriate? Anyway, you have to decide the shape of variable cost. How do we represent the shape algebraically? Here is one cost function that we might choose, right? First example is variable cost is equal to BQ, right? BQ. Variable cost is beta Q. Simply beta Q, linear relations. Q increase, then variable cost increase with constant rate, right? You can choose this one. Or if we wish to allow U-shaped average cost curve, you have to define BQ plus gamma Q scale, right? Then variable cost shaped like this, mathematically. If the marginal cost curve is not linear, in that case, marginal cost is equal to beta plus 2yq, right? So linear. If marginal cost curve is more than linear, we might use a cubic cost function. Usually, theta q like this. Right? If with delta, delta like this. If we assume this kind of variable cost, we can think about then marginal cost, average variable cost. Average variable cost is variable cost divided by Q. So beta plus gamma Q plus delta Q square. That is average variable cost, right? And marginal cost is first derivative of variable cost with respect to Q. Then beta plus 2 gamma Q plus 3 delta Q square. That is marginal cost. Okay? I'm sorry. Okay, cost function as a measurement of scale economies. I already explained this scale economies of index, right? Scale economies of index. Scale economies of index, SCI, right? Is 1 minus EC, right? So if this one is positive, economies of scale. This is negative, this economies of scale, right? SCI is defined as follows, right? Average cost, marginal cost curve is like this. Average variable cost is like this, right? And cost function implies the average and marginal cost curves are U-shaped in this cubic function, right? And cost function for electric power. In 1955, the consumers bought this billion kilowatt hours of electricity. In 1970, they bought this one, right? 1955. What this increase due to economies of scale or other factors? If it was a result of economies of scale, it would be economically inefficient for regulators to break up electric utility monopolies, right? So anyway, production increased compared in 1970, this amount, 1955, this amount increased greatly. Why that happened? Some people said economies of scale. If this kind of thing, economies of scale matter, it would be economically efficient for regulators to break up electric utility monopolies. So think about Hanjeon in Korea, right? It's a one company, but after because some monopoly problem, this one is split into many branches and something. If that kind of some government policy is correct, only when there exists no economies of scale, diseconomies of scale, right? But if we can find economies of scale, this kind of breaking of electric utility monopoly is bad decision, inefficient, okay? So the cost of electric power was estimated by using a cost function that is somewhat more sophisticated than the quadratic and cubic function discussed earlier. So anyway, they calculate that. And they calculated scale economies index, right? Scale economies index. What is this? I forgot. Scale economies of index. S equal to 1 minus EC, and EC is equal to MC over AC, right? This one was MC over AC. Then that is AC over MC, isn't it? Right? So using this one and this kind of form, we can calculate this one, right? Average cost and marginal cost. And value of SCI estimated is this one, 0.41, 0.26, 0.1, 0. Like this. What's the meaning of this? We can empirically find economies of scale is positive. Scale economies index is positive. In other words, economies of scale occurred in electricity company. So, breaking up monopoly company into many companies is not efficient. That is conclusion in the United States. I think almost same in Korea. So average cost of production in the electric power industry. The average cost of electric power in 1955 is this one. And achieved a minimum at approximately 20 billion kilowatt per hour at point A, I think. But by 1970s, the average cost of production had fallen sharply and achieved a minimum at an output of more than 33 billion kilowatts, 33 billion watts, this point. Okay? So average cost decreased greatly. Okay, now appendix left. This appendix is really important. So now think about this one, right? Cost minimization. From cost minimization, more generally, this one. Okay, this one. When there is cost minimization, when Cobb-Douglas production function is Cobb-Douglas, okay? Then solving this one, we can derive optimal labor demand or optimal capital demand and minimize total cost. I'd like to explain this in 1 minute later. Okay, finally, I'd like to explain some mathematical one killer question, right? So, Cobb-Douglas cost and the production function. So, anyway, in consumer theory, we solve maximization of utility when utility function is Cobb-Douglas, right? Utility is, I forgot, C1 alpha, C2 1 minus alpha, C2 beta, subject to budget, P1, C1 plus P2, C2 is equal, and you find, so C1 star, C2 star, right? Mathematically. In consumer theory, you find this one, solve this one using Lagrangian function methodology, right? You construct Lagrangian function and you derive 3 first order condition and 3 first order condition solved simultaneously to find optimal demand for good 1, optimal demand for good 2. We studied similar thing today, right? Cost function with minimizing cost. Cost function is WL plus RK, subject to production amount, right? Production function is Q is equal to A K alpha L beta, right? That is correct. Okay, like this. And find K star, L star. We can find this one using Lagrangian function methodology, right? So the step number 1 is construct Lagrangian function. For example, Lagrangian function pi is equal to this one, WL plus RK, right? Minus lambda A K alpha L beta minus Q, right? Alpha minus Q. We construct Lagrangian function first, then we calculate 3 first order conditions, right? Should be equal to 0. This one is equal to 0, and next third variable is lambda, right? Should be equal to 0, right? First, try first this one, right? Here, a partial derivative of Lagrangian function with respect to L. Only labor is variable. The others are constant. Then first, so this one is W only left. This one disappeared. Minus lambda, and this only this one is variable, right? So beta A K alpha L beta minus 1 left. This one is just constant number, so disappeared. This one should be equal to 0, right? And next, this one. Partial derivative of Lagrangian function with respect to capital star. Then only capital star considered as variable. Then this one disappeared. Only R left. Minus lambda. What is this? Alpha in front of here. A, K, alpha minus 1, L, beta should be equal to 0. This one disappeared. Okay? And third condition is this is variable, that is constant number. So all in that case, what happened? A, K alpha, L beta minus Q, right? Q0, Q anyway. Q0 is constant. Q is variable, so Q0 in cost minimization. But anyway, this one should be equal to 0. So we find 3 first order conditions. W is constant numbers, right? Because perfectly computative market. R is constant numbers. Beta is constant number. Alpha is constant numbers. Everything is a constant number except three variables, L, K, lambda. And we have three equations. So we can solve this equation simultaneously, right? Okay, then what is the next process? Okay, for example, first think about this. This one means, now think about this. AK alpha L minus beta. This one, right? Only this one. A K alpha L beta minus 1 is equal to A K alpha L beta divided by L. Right? This one L beta divided by L. Can you understand? And we know this one is equal to Q0. So this one is Q0 over L. Right? So from here we know W, wage rate, is equal to lambda beta Q0, right? Over L. Can you understand? From here, we said this is 1 prime. Similarly, this one is AK alpha minus 1 L beta is equal to AK alpha divided by K L beta, right? And this is equal to Q0. So this one is Q0 over K. This one is Q0 over K. Then R is equal to lambda Q0 alpha Q0 divided by K. Right? Okay, same thing. Can you understand? That kind of thing. And from here, we know AK alpha L beta is equal to Q0. Right? That is 2 prime, 3 prime, for example. From here, we know lambda from 1 prime. Lambda is equal to what happened? Lambda is equal to WL over beta Q0, right? WL over beta Q0 from this one. And from here, lambda is equal to RK over alpha Q0. So that is from 1 prime. That lambda is equal to this one is 2 prime. So this one is equal to this one. Right? Then from here, K over L is equal to beta over alpha, and Q0 disappeared, and that is W R, right? Alpha beta W R and K left, right? From these two, we can get these relations, right? Or capital is equal to alpha over beta W over R L. Same thing anyway, right? Then this one over this one should be inserted here, number 3. Then we can get capital or labor, isn't it? Right? This one inserted there, then what happened? For example, L is beta alpha R over W, K. This one inserted to 3 prime. Then Q0 is equal to, can I say? Right? 3 prime is, what was 3 prime? Q0 is equal to AK alpha L beta, isn't it? And this one inserted here, then Q0 is equal to A, K alpha, and L is this one, right? Alpha, beta, this one, and K, this one, beta, isn't it? Right? Or this one is Q0, right? And this one is equal to, what can I say? A moving there, then we know like this, right? And this one is K alpha, K in front of here, K, and alpha, beta, R, W, right? I'm sorry, K beta, and the remaining beta is equal to Q0 over A, isn't it? Right? This one is K alpha plus beta is like this. Right? For example, like this. Then this one multiplied by this one is this one. Then K alpha plus beta is equal to Q0 over A, and this one moving there. This one moving there. Then that is minus beta. This one upside down, then beta gamma alpha W beta, right? So that is alpha W beta alpha alpha W beta. This one moving inside here, then this one minus reverse value of this one, and beta still remained like this, right? From here, K star, optimal demand for capital in cost minimization solution is A Q0 1 over alpha plus beta, and this one beta over alpha plus beta, alpha W beta R. So optimal demand for capital is represented by the just constant numbers alpha and beta, Q and A, W and R. Okay? So that is demand for capital or optimal capital employment. This one inserted here, then we can get L star, right? Then L star is equal to beta, gamma, alpha, W, and K. K is this one. A, Q0, 1, alpha plus beta, and beta, alpha, alpha, W, beta, alpha plus beta, isn't it? Right? So this one, is equal to alpha W over beta R minus 1, isn't it? Right? Then Q0A 1 alpha plus beta and alpha W beta R, right? Beta alpha plus beta minus 1. Okay? Then this one is 1 alpha plus beta, beta R alpha W, alpha plus beta, beta minus alpha minus beta. So then minus alpha left, right? Minus alpha left. So L is this one. Then Q0 over A 1 alpha plus beta, and this one, as I said before, alpha W beta R, that is alpha plus beta. Okay, that is L star. So we calculated L star and K star like this. Okay, so we derive L star and K star. Then we can calculate minimize total cost there, right? So minimize total cost, we can say C star is WL star plus RK star, isn't it? Right? Then WL star is this one, right? And RK star, K star is this one. Then we calculate minimize total cost. Okay, that is mathematical explanation of cost minimization. In this process, we can derive optimal labor demand, optimal capital demand, and minimize cost like this. Okay, I'd like to stop here.